in polyelectrolyte complexation and noting the kind of polymer environment that's created by polyelectrolyte complexation may more closely resemble what actually happens inside a cell rather than water. And in fact, if I blow up one of those figures, you can see that the rate of polymerization of actin in a polyelectrolyte complex is orders of magnitude greater than it is in pure water. A group of people at MIT, including a much older former group member of mine, Arup Chakraborty, have been looking at how this kind of biological condensate might control transcription, creating local environments for enhanced protein transcription. Now, this is a functional part of a cellular apparatus. So these are some of the reasons that the interest in this field is maintained and growing. The slide advancer stopped advancing. Can I just ask for the next slide? Could I ask that the clock be stopped? It is, the clock was stopped. While that's coming back, I know what the next slide is. It's a very early theoretical model of what the salt versus polymer concentration phase diagram for liquid-liquid phase separation in polyelectrolyte complexes should look like. And it was created in the late 50s by Theo Overbeek and a student named Lorne, who essentially took the Fleury-Huggins entropy of mixing and added to it a Debye-Huckel term for electrostatic interactions in a certain volume. And this predicts a very plausible looking phase diagram that has a two-phase region, a critical salt concentration, and predicted tie lines that predict what supernatant polymer and salt concentration is in equilibrium with the dense phase polymer and salt concentration. And we set out to test that because it had never been tested before. This is the diagram that I'm describing rigorously. And by that, I mean actually measuring in detail the polymer and salt concentration in each of the branches of the low polymer concentration and the high polymer concentration. Different people have done different things, and I think reached superficially plausible but incorrect conclusions about the phase diagram, especially the slope of the tie lines, which seemed implausible to me that there was more salt volume in the dense phase than there is in the supernatant phase. But hold that thought. So in order to study this, we wanted to use a model system. And for that, we chose polylysine and polyglutamic acid, the two central polymers there, because they have identical backbone, achiral version, and L-glutamic acid. One can use racemic mixtures so that there is no chirality or secondary structure that could lead to hydrogen bonding. And we started out by looking at equal molecular weights and equal composition, equal concentrations of the polyanion and the polycation. And we got this diagram, which if I could advance the slide, I'd show you. There we go. That looked like this. And you can see that the two-phase region increases with the degree of polymerization of the two polymers. On the right-hand side are the same data plotted on a logarithmic horizontal axis, so you can see that the polymer concentration in the supernatant phase isn't exactly zero, which was a simplifying but incorrect assumption used in some other studies. But the main thing that we focused on